Hello, everyone. Thanks for joining us. My name is John Goss. I'm former president of the Astronomical League, and I'm here today with Bill Stein, board member of AAVSO, and he's going to be talking to us in a few minutes about the organization and about variable star observing and such. This presentation is part of a series that we're conducting to help celebrate the Astronomical League's 75th anniversary. The league was founded on November 15th, 1946. So we're coming up in another few months to that special anniversary. So we're happy to bring all this stuff to you to try to show what the Astronomical League is all about while encouraging people to join this amazing hobby of ours of amateur astronomy and its many facets. One of those facets is variable star observing. And there's no organization better to talk about this than the AAVSO. So I'm very happy to have Mr. Stein with us here today to talk a little bit about what he has done and what the organization's all about. Bill, welcome aboard. And I'm going to allow you screen sharing permission. So if you'd like to say a few words about the organization and yourself and whatever, and give your presentation.
Okay, yeah, I'll just say that my background is astronomy. I went to University of California at Berkeley, got an undergrad degree in astronomy, and then went to Indiana University, where I got my master's and a PhD in astronomy. And then from there, I worked for the government, believe it or not, as an astronomer in the federal government, working with the National Reconnaissance Organization, which does looking with telescopes, but instead of looking at stars, looks down on the Earth. So we can't talk too much about that, but they do need astronomers in that, believe it or not. So right now I'm retired and living in Las Cruces, and I'm enjoying life as an amateur astronomer again. I have my own observatory, and so I've been looking at variable stars, and I would like to talk to you about that. So let me look at our presentation. Okay, the talk is called Why Observe Variable Stars, and I hope during this talk to be able to answer that question. So let's take a look at what are variable stars. And you can see the definition is stars whose brightness is changing with time. You know, on time scales that we can really measure, such as hours, minutes, days, years, something like that. And it's respect to stars whose brightness is not changing. So we need a comparison star and usually a check star to look at. Although some stars we can actually see with our unaided eye that are varying. For example, back in October 2019, Betelgeuse here, the brightest star in Orion, started to fade out of sequence. It wasn't supposed to start fading. And then I started noticing on my own back in December of 2019, boy, Betelgeuse is starting to get pretty dim, not what I've usually seen. And it really dimmed by a significant margin in magnitude, so that by the time we came into January 2020 and February 2020, it was very, very dim. And what we finally determined, I guess the Hubble telescope was able to see that Betelgeuse actually expelled a large gas cloud that went around and cooled and started to dim the Betelgeuse star. So that's how we sometimes come across variability that we're not expecting. So it is kind of an interesting science to be a variable star observer. So let's look at the classification of variable stars, and you can see that we have two major categories. The first one is intrinsic, and these are stars that vary from something happening internally to the star in the production of its energy. So you can see you have pulsating stars and then eruptive stars. The cataclysmic stars are the type that I've been observing, cataclysmic variables, such as dwarf novae, recurrent novae, and so on. And it turns out that Betelgeuse is also in that type of variability there, and also up here in the pulsating stars. You can see when you go to the long period variables, you come into Mira type and semi-regular. And Betelgeuse is really a semi-regular pulsating star. It's a giant star, a red star. If you put Betelgeuse, where the sun is, it would extend beyond the twice the orbit of Mars. So it's really a extremely large star. And we know that it is variable. So even the sun is considered a variable star because of its changing sunspots. The cycle is 22 years, 11 years, and then you switch polarity and back again. So it's a 22-year variable. Our organization, the American Association of Variable Star Observers, you can see we have observers throughout the world, and even in Australia, which you can't see right here, but we have about 1,400 observers who are members, and we have a number of observers who contribute who are non-members, but we do try to encourage people to join us and submit their observations to us. So what is our tool for studying the night sky? It would be a light curve, and you can see it here. Usually, of course, we don't connect the dots in straight lines, but we try to get a curve through them, and we look at the changing of the light intensity. We call that a light curve, and the measuring of that is called photometry or light measurements. And we can do it in a variety of ways. You can see with binoculars, naked eye, like we did with Betelgeuse, with a digital camera, or with telescopes. And also we can start using cameras attached to telescopes. I use a CCD camera, but I'm going to be transitioning to CMOS. That seems to be the way the cameras are going for astronomers, is to the CMOS type. So you can see that we have a very, very large database and continuing to increase. We have over 42 million observations and counting. And of course, we make sure that we vet or we validate any observations that come into our database. And professional astronomers do use the data. And if they do, and they sometimes publish a paper from that, they may include some of our observers as co-authors on the paper, which is a really nice thing to do, to get credit for your observations. Now let's take a look at the different types of things that we learn from looking at these the variable stars. So let's see, we have different spectral classes for stars. I'm sure a lot of you know this: O, B, A, F, G, K, M. And the mnemonic that I use is, oh boy, an F grade kills me. I did get one F grade, I guess, in college, but it would kill you. So that's a good mnemonic for that.
Perfect. I love that. That is perfect.
And we can determine, as you see, going from the O class, those are the largest and the hottest, down to the M class, which are the coolest and the smallest. Although Betelgeuse is an M star, it is not a main sequence one. It is a giant star, so it's pretty large. But we can determine things from looking at the variability of stars, like the mass, the radius, the luminosity, temperature, sometimes even the internal structure, how the star actually functions in producing its energy. And of course, magnetic fields and how stars evolve. One of the things I am interested in, of course, is determining the cosmic distance scale. And you can see here that if you start at the bottom of this triangle, you have the most accurate, and you go up to the top, you have the least accurate methodologies for determining distances. But we use the Earth's baseline for parallax. And then when we go to stellar parallax, we use the Earth's orbit. And we have something called a parsec, or the parallactic angle of parallax for 1 arc second, and that's called a parsec, which is about 3.26 light years. So we use the parallax, which is pretty accurate, and then from there we go out to different variable stars, and we have our Lyra variables for determining distances. They are used because they have a constant magnitude, absolute magnitude, and it changes, of course, with the relative magnitude or observed magnitude as you go with distance, and we can calibrate the difference between observed magnitude and absolute magnitude to get distances. And then when we go farther out in distances, we can use Cepheid variables, which are observed even external to our own galaxy, out to Andromeda and other nearby galaxies. We see Cepheid variables and we can calibrate distances there. And finally, we go to type 1a supernovae, those explosions, and we can calibrate looking at the light curve, how far away those are. So you can see those being RR Lyrae Cepheid variables and type 1a supernova, that we use the variability of the stars, the observations that we as observers in the AAVSO determine to help determine distances. Now go ahead.
With history, I know that the Cepheid variables were used for the determining Andromeda galaxy's distance. About how far out does that work? I say you have it in kiloparsecs, but do you know in light years, how many million light years would this be a useful tool?
Well, I think
I don't know.
Cepheid variables, we're talking probably about to maybe 70 million light years.
It must be
fairly far out.
Pretty tough to measure that.
Yes, but you could do that if you have the right telescopes, I guess.
Good. Thank you.
Yeah. And then the type 1a supernovae, and then out beyond that, you go use Hubble's law, which means you're looking at the redshifts in the spectrum, spectral shift of the H alpha line, for example, in the galaxies. But at least you can see here that variable stars, measuring them is useful in helping determine the cosmic distance scale. So that's something that a lot of us try to do. So let's look at a couple of these things, measuring the distance with Cepheid variables. You can see a light curve and the pulsating Cepheid variable as it gets smaller and brighter, and then larger and dimmer, and you can see it changes colors also as it goes through this cycle. And we have something called the period luminosity relationship. That is, if you measure the period of a Cepheid, then you know its luminosity in an absolute sense, and you can then, measuring the period, determine how far away a particular Cepheid is, and then, of course, if it's in a galaxy, how far away is that galaxy. And like you say, that was done first for the Andromeda galaxy by Hubble, who determined that it was really external to our own Milky Way. So that was the beginning of our understanding of our universe. Okay. Now let's take a look at the supernovae. We're looking at particular the type 1a. There are a variety of different new supernovae, but the type 1a is interesting because it's generally predictable, and it consists of a binary system with a white dwarf, and another could be a low mass cool star, or even sometimes another white dwarf. And of course, when you get beyond 1.4 times the mass of the sun with the mass of the white dwarf, then interesting things happen. Generally, like the sun, it'll turn into a white dwarf and just contract into that degenerate star. But if you're larger than that, then there's unusual things can happen, especially if there's in a binary system and one of the stars gets absorbed by the white dwarf. You can have explosive things happening. So we do measure the supernova when it occurs from this type of situation with the binary and the white dwarf. And again, we have what are called standard candles, just like we did for the RR Lyrae and the Cepheids. We know in general, not always, but I would say more than 90% of the time, that if it's a type 1a supernova, the light curve is pretty standard and reaches a certain absolute magnitude, and the shape generally is what we see here, that we've sort of contracted by a logarithmic time scale here. So we can use that to also help us determine distances to objects far away. So this takes us out a little further, as you can see here, with the measuring of the supernovae. We're going way out to, into the gigaparsecs, into the billions of light years that we can do. So this takes us out to many, many other galaxies close to the beginning of the Big Bang. So if we look at the supernovae, the physicists in 2011 got a Nobel Prize for the discovery of the accelerating expansion of the universe through observations of these distant supernovae, just checking them out, seeing how far back they could go, and looking at the acceleration. So these are important objects for determining how the universe actually began. Cosmology is the name of the study we have for the understanding of the evolution of the universe. So cosmology is another study where variable stars could contribute. Then we go to something else that I've been finding very interesting lately, because most of the time when we look at variability, we're looking at light, the variability of light in stars. However, something happened back in 2017 with something called LIGO, which is standing for that's the Laser Interferometric Gravitational Wave Observatory. And these were some gravitational wave detectors that were set up, and they actually detected the combination of a couple of different types of objects, a black hole in one case, and in another case, neutron stars. And when they combined, they sent out these gravitational waves that were detected. And this was another way of detecting information from stars or other objects other than light. So this was the first time that we observed something like this. And this is a result of the they got a Nobel Prize in 2017 for this particular thing. The types of objects we see from this, we do see the afterglow effect visually. So we can detect, if we see a gravitational wave detection event, sometimes we can see it observationally with telescopes in light also. So it's important to know when these things happen. Usually they're binary neutron stars that merge together. Sometimes a binary black hole that would merge, or neutron star black hole events. So there's a variety of things that happen. These are usually way out in very distant galaxies, but this is another way that we can observe and understand how the universe evolves. So the formation of heavier elements than hydrogen and helium. This is an interesting thing that we consider in astronomy, that in the beginning, the Big Bang, that there was mostly just two elements, hydrogen and helium, in the universe. But as stars formed, primarily they were hydrogen stars, they were able to generate different types of elements. And you can see some of them on the table here. So the Big Bang fusion is in blue. Those were the two elements. And then low mass stars started producing other elements. And then exploding massive stars like what we call the supernovae produced these other elements. So and then cosmic ray fusion. And then the latest thing, we didn't know how some of these elements in the purple color were created until LIGO, when we learned about the merging of the neutron stars and things like that, black holes. Those particular elements were created from that particular explosion.
Bill, I think that this is a very fascinating graph or chart that you have here. I've never seen it like the periodic chart expressed like this. And yeah, you're talking about the heavier the elements. Of course, my eyesight immediately goes down to something like gold. Where does gold come from? And I didn't know that merging neutron stars played a big role in that.
It played the majority of the role in that. Yeah, iridium, things like that. They did not originate in the normal way we think of. Yeah, so this is kind of an interesting chart to explain how the elements were created, starting with the Big Bang. Yeah. So another thing we look at in variability of objects is planet formation. And of course, this can be observed because if you have an exoplanet and it transits a star's surface, we can see the star dimming in light. So we can actually look for variability caused by an exoplanet. And this is how a new area that we've been looking at. We have, I'll get to that in a little bit. We have people who really like to look at and search for exoplanets. And one of the ways to do that is by variability of certain stars. So this is a big area in variable star observations, and it's also big in with professional astronomers too. So how can you be a part of the AAVSO? If you can, use your eyes, look through binoculars, look through a telescope, and you don't have to have sophisticated equipment, you may be able to contribute to our database with your observations. Although you may want to eventually get into more sophisticated equipment like I have, which is a CCD camera, and then you can do more precise observations and generate light curves like you see at the bottom here. But really, it doesn't take expensive equipment to really contribute to variable star observations. So don't be concerned if you don't have the professional or expensive equipment. Do it with your binoculars, with your eyesight, just like we saw with Betelgeuse. You can look for those changes in observations or changes in brightness. So let's take a look at the AAVSO website. I want to spend a couple of minutes on that before we conclude here, but you can see this when you come to our website. This is traditionally what you would see when you come here. If you scroll down a little further, you come to these resources that I like. You can go directly to certain things on the resource page. I use the variable star index a lot if I'm searching for a particular variable star I want to observe that night. You can also take your observations once you've completed them and plot a light curve. And we do have a journal. You can look at articles. And then, of course, if I want to submit my observations, I can submit them, and they can be checked by our people at the AAVSO organization to make sure everything is copacetic there. Now, another thing you may want to look at are the observing sections. So maybe you have an interest in a certain area, and the observing sections might help you out on that. So, for example, the first one here is the Bright Star Monitor section. I have one of the Bright Star monitors at my observatory up in the mountains nearby. And so people like, amateur astronomers or citizen observers is what we really like to call them instead of amateur astronomers. Citizen observers can apply for time on the Bright Star Monitor for a project. If they have a particular star they may want to look at, they can take their project and get the Bright Star telescope to look at the objects and send them the results, and then they can process it and do their own variable star work on it to determine the period and things like that of their star. So I would recommend, if you're interested in starting out, maybe look at getting some time on our Bright Star Monitor. And cataclysmic variables, that's an area that I like to observe in. You have a whole section of that. Eclipsing binaries now would include, besides double stars, you could also include the exoplanets. So that's a new section right below that. And instruments and equipment. If you want to understand how better to use your CCD or now the CMOS cameras, we have a section on that. And long period variables like Myra and Betelgeuse. We have even some people who still use photoelectric photometry instead of the CCD. We also have short period pulsating variables like the Cepheids and our Lyra. We have some who, if you don't want to have equipment to look at night and you rather look during the day, we do have a solar section where you can look at sunspots and things like that and then record them and send them in. We do have a new area, spectroscopy, looking at variability using the spectroscopes, and finally the young stellar objects. So we have a variety of areas where people might be interested in looking and determining where they might fit in with their observations or with their interests in certain areas. So also going to the next part of the page, let's say getting started. You've just joined, you want to see what the AAVSO has to offer you. So you can go up to the top here and look at getting started. And that'll tell you what are variable stars. You have some tutorials, manuals, even find a mentor. When I first joined the AAVSO, I did use a mentor to help me on how best to use my equipment. And there's how-to videos too. So there's a variety of ways to help new members to the AAVSO. So we can also look at what's in the community area up here. This is an important area where if you're interested in our meetings, what's happening at our next meeting, forums, there's a number of different forums where you can participate and see what people are doing, or even ask a question and then have a discussion in the forum. You can find a member or an observer. There's AAVSO communications and events. Now the communications and events, there are webinars, things like that. So there are a lot of free things, and we have webinars almost monthly on a variety of different topics, which I think would be of interest to most people. So why observe variable stars? I think if you want to satisfy your desire to contribute to science, which a lot of us do, you can do that by helping to determine the cosmic distance scale, like we saw, by observing the RR Lyra, Cepheids, and other types, and learn about stellar evolution. You could even help by looking whenever a supernova occurs. If it's bright enough, you can actually try to help participate in tracking the light curve of the supernova. And then understanding the origin and evolution of the universe, again, applies to our supernova. And finally, search for life in the universe through looking at the exoplanets transiting the stars and determining where they're located. They might be in the habitable zone of that star, where you might be able to have small enough planets like the Earth where life might survive. So we encourage you to explore the universe with us together and join us at the AAVSO. So thanks for your participation. And I guess if there are other questions, I'll try to answer them, John.
Yeah, thank you, Bill. That was all very intriguing. One thing I didn't realize, or I didn't understand, is the wide field that variable star observing has, the wide field in astronomy, such as, what I mean by that is, such as you were talking about expansion of the universe, and gravitational waves and all that. That is cutting edge, high technology stuff. And I didn't realize that this played a role in that. And then you were bringing up the whole new wonderful field of exoplanets. That by itself is really cool. And I think most people could really get into that, finding other worlds out there. Variable star observing, or that type of observing, would certainly benefit that field. And also what struck me when you started out about Betelgeuse, Betelgeuse, extremely easy star to see. It's one of the brightest in the sky. And yet here it is giving this weird behavior, and it's throwing the whole community into a tizzy, trying to figure out what's going on. And that is something just about anybody could do, could participate in. And I'm not a big variable star observer, but even I went out and I could see the changes in Betelgeuse, comparing its brightness to stars, to neighboring stars, and I could see, hey, it's dimmed quite a bit. So as I said, I'm kind of struck by the wide field that this type of activity has. And another thing I just wanted to bring up was You mentioned you had about 1,400 members of the organization. And if you're an amateur astronomer, you often hear about variable star observers cataloging or have 10,000 observations or 20,000 or even more. Wow. Well, I mean, it must be a field which people really get into and get deep satisfaction from conducting all these observations.
Oh, they do. But now, with the cameras like CCD and CMOS, I can maybe observe a couple of stars, maybe look at one particular one all night and get hundreds of observations a night, maybe 600 observations a night. That's why people really come up with these large numbers of observations. It's only because we have the technology now to do that.
Well, plus the field is advancing with technology. So 10 years from now, who's going to know? Who knows how it's going to be? But this is fascinating because, here you were talking about all the different causes of variability. Some aren't really variable stars. It's just a circumstance they have with other stars and so on. And it's fascinating that anyone can play a role in this.
Exactly. Yeah. And so we encourage people to participate if they're interested.
You bet. You bet. Well, on that then, unless you have something more to say, I think we can conclude here. And Bill, I think you did a great job in explaining this, and not just explaining it, but getting people's enthusiasm going on it. It cleared up some points in my mind about what the organization actually does and offers, and it's pretty clear. So thank you for taking your time and putting together this presentation and giving it today. I really appreciate it, and I think our members out there are going to get something, find some value in this, get something out of this, and maybe they will be persuaded to try their hand at variable star observing. Anyway, I appreciate the time that you've given, and unless you have something more to say, I think we'll sign off here in cyberspace, and maybe our paths will cross again. And for those who are watching this, please keep in tune for the other programs that we will be offering as well. So thank you, Bill, and we'll see you later.
Thank you, John, for the opportunity.
Bye.